Hi, everyone. Thank you for tuning into today's micro lecture. We're going to present a visual of compounded growth versus non-compounded growth, or what we call linear growth. Sometimes it can help to look at a graph and think about what compounding means over time. Now, remember, compounded growth just means that we're reinvesting gains. So we're generating gains on gains, or sometimes we call that interest on interest. And that growth is going to be exponential. So when we look at the formula for generating the future value of a given sum when the returns are compounding, we're using exponential in the formula. When we're not reinvesting the gains, the growth is linear. It's just going to be a straight upward line in the amount of the return. And the return accumulates in the account, but it's not reinvested, so it's going to grow at a fixed amount. Let's just look at an example of a simple return and how that just generates linear growth. So Joe makes a $50,000 investment in an account which pays 10% per year. How much will the investment grow in 20 years if the 10% annual return is not reinvested? So all we do is we take the $50,000 investment and we add the gain to that. We generate the cumulative gain, the total gain over that 20 years is just 50,000 times the 10% per year times 20 years. And then we add that to the original amount, we get 150,000. Now let's look at a graph with that return, because those returns are not being invested. That return is just growing at that 10% on the 50,000. That fixed amount every year. So it's just an upward straight line that grows at a constant rate every year. Now let's look at a compounded return. We'll take that same example, the $50,000 investment over 20 years at 10% per year. And this time we'll reinvest the returns at that 10%. So we know the formula. We've gone over this in some previous lectures. It's just the present value times 1 plus r to the nth power. This is where we get the exponent from. It's that n. So the time here is going to be up in that exponent. Plug these variables into that formula, and we get a compounding factor of 6.7275. We multiply that by the $50,000 investment, and we get a future amount of $336,375. Now let's look at this graph. Is the $50,000 invested where the returns are compounded, and what do we see? It grows upwards, so it's not just a straight line. So it kind of starts out looking like a straight line, but then it curves upwards, and that curvature really seems to increase in these later years. And that's one of the really important things about compounding, as we'll see even more so in the next slide. It's how this accumulation works in the later years. This, to me, is probably the most important graph that we can look at when we think about compounding. So here on the bottom, the line is just that linear return. The returns are not invested. And then this top line is our exponential growth, the compounded return. And what we see is as time goes on, as we move to the right, as we get further and further out in those years, that discrepancy between the compounded return and the linear return grows. And if we kept going beyond that 20 years, this difference would be even greater. And that's the power of compounding. So when we start early and we let our gains reinvest over time, that money just grows and grows and grows. That's why financial planners, financial advisors always talk about, starting early, giving yourself a long runway. We're going to end that here. Thanks for tuning in, everyone, and we look forward to seeing you on the next lecture.